Okay, starting to look at calculus, chapter 601. So first ever calculus is understanding gradient. And up to this point, we've always looked at gradient to be the steepness of a line, and generally it's been a straight line. So you should be quite familiar with this formula here, and it measures the rate of change of our y variable with respect to x. So it's basically saying how much does y increase or decrease as x moves along. So we have the equation of rise over run, or difference in our y values divided by the difference in our x values. So notice that when the gradient of a straight line is positive, as this example is here, the gradient is increasing, so we get a positive gradient. And when gradient is negative, the line is decreasing, so it'll be going down as we move in the right, towards the right. So straight lines increase or decrease at a constant rate, and the gradient is the same everywhere on this line. So it doesn't matter what 2 points we would pick on this line to determine the gradient, we would always get the same number. So let's have a quick look at a couple of examples of straight line gradients, just a bit of a refresher. So part A, the graph shows the distance traveled by a car over time. Find the gradient and describe it as a rate. So as we said, our gradient, or we use m to describe gradient. M is equivalent of rise over run. So this would be my difference in y over my difference in x. So as you can see, I've rose from 0 up to 400. So 400 would be difference in y over, I've gone across 5 hours. 400 divided by 5 gives me 80. So I could safely say, as expressing this as a rate, this car is traveling 80 kilometers per hour. Part B, the graph shows the number of cases of flu reported in a town over several weeks. Find the gradient and describe it as a rate. So again, we're looking at a straight line here. So we're going to do our difference in y, divide our difference in x. So my gradient here equals, now we have a negative gradient, so I'm going to get a negative result. So I started at 15 up the top, I end at 0. So I've got negative, I moved 15 in the negative direction, and I moved across 10 weeks. So negative 15 on 10 is the same as negative 3 on 2. That's not a 2. Negative 3 on 2. So I could safely say that, find the gradient, describe it as a rate, that the number of cases in the hundreds is decreasing at 3/2 every week. Cool. So, I mean, finding gradient and straight line graphs is all well and true. But when we're looking at functions, our gradient is not always the same. And you can see that comparing the graph on the left here to the graph on the right. So if we were, one is a straight line, other is a curve. So is the average speed of the bicycle the same in both cases? Well, yes, it would be the same, because we would still have to find our difference in y divided by our difference in x. So in both cases, it's 20 on 4 or 5. But the difference is that the speed in the graph on the left, if we took different triangles, is always constant. So when we're looking at a straight line, our gradient is always constant. But when we're looking at this curved line over here, our gradient, or our speed at which it increases, always changes. So in this case, we're starting off very slow. We then get quite quick, or the gradient increases around the 2-hour mark, and then it tapers off again towards the end. So we're asked ruler, yeah, got a ruler. So we're asked, how could you measure the speed in the second graph at any one time? Does it change? We answered that. If so, how does it change? We kind of answer that. And the answer would be of how we graph it is we would draw tangents at various points throughout the graph. So a tangent is a line that runs, that's not a very straight line, but it runs across, it runs in direct parallel to the touch. So we could actually then use our tangents to calculate the gradient at any point. And as you would notice, the steepness or the gradient of our tangents would change as we move up and down the graph. So this is a simple squared function. So this would be such as x squared. It'll have to be minus a number, considering we're below below 0. So the gradient of a curve shows the rate of change of y as x changes. So a tangent to a curve is a straight line that just touches a curve at one point. So you can see there are 3 tangents here. There's touches on the left, on the bottom, and on the right. We can see where the gradient of a curve is positive. So we can see the gradient of the curve is positive on the right, negative on the left, and the gradient is 0 at the bottom, or in other words, it is not increasing nor decreasing. Notice that when the curve increases, it has a positive gradient. When it decreases, it has a negative gradient. And when it is a turning point, or down the bottom here, it has a gradient of 0. So further onto that, we're asked to copy each curve, or we've got a curve here. We must write the sign of its gradient along the curve. So at this first, the leftmost of the graph, we have positive gradient. So the graph is increasing over time. So it will be increasing all along here until we hit our 0. So this would have a gradient of 0, or it will be a turning point. The gradient then changes and the gradient is now negative, or as we move right in the x direction, we're decreasing in the y direction. And then we get down to another 0 or another turning point, at which time our gradient changes. It is now positive, last turning point, and then it is negative all the way down to the end of our graph here. So that's how we'll go about completing that question. And the reason why we do it like this is because this then helps us graph our gradient function. So I'll explain more about that here. So find the gradient of a curve by measuring the gradient of a tangent to the curve. We can then sketch the graph of these gradient values. So up until now, when you're dealing with functions, you've seen them in the form of f of x equals, or y equals, or they're sort of the main ones. So f of x or y. We're now introduced to this new notation here, which is f dash of x, or wherever you see f dash x or y dash, the dash is talking about the derivative. So in this case, it's the first derivative. Later, or right at the end of the chapter, you'll be introduced to the second derivative, which is indicated by 2 dashes, but we're not going to focus on that right now. What we're focusing on is our single dashes, or our gradient functions, or derivative function. So essentially, when we find the derivative, or when we're finding f dash of x, we're finding the gradient function, or we're basically finding a function that we can plug values of x in that'll tell us what the gradient is at that point on the curve. So let's have a look at another example here. So in this example, they were asked to graph the gradient function, or they were asked to graph f dash of x of this function. So as you can see, our function itself is x squared. And that's quite a common graph that you're all used to. We can see the gradient starts off as negative to a turning point at 0, and then becomes positive. So over on the right side here, we have graphed the gradient function of f of x, or x squared, which would actually be 2x. So as you can see in this instance, our gradient function is a straight line, or it's a linear equation. And we can substitute, or we can identify what the gradient is at various values for x. So in this case, y represents our gradient. So if I said, what is the gradient when x equals 2 of this function, I would move up and across, and the 4 on the y-axis would tell me, well, the gradient is 4 at x equals 2. So if I were to go back to my graph here, when x equals 2, or at this point, if I drew my tangent along my curve, and then I used a triangle to find its gradient, I should get 4. So we would have maybe something like 8 over 8 on 2, something like that. Okay, so in this exercise, you'll be doing a lot of sketching gradient functions, and they can be quite tricky, but there is a method to the madness, I guess. So first part is you want to mark on the original curve where the gradient is positive, negative, and 0, which is what we did in that first exercise. So I'm going to go along and mark along my curve what the gradient's doing. So it's positive leading up to a turning point, then becomes negative leading down to another turning point at the bottom, positive again, working our way up the other side of the graph, 0 at the top, and lastly negative. So we've completed question 1. So we marked on what our gradient's doing as we move across the graph. I then place the points where m is 0 on the x-axis, and remember m stands for gradient. So where the gradient is 0 on our derivative graph or on our gradient function graph, I need to mark my zeros in. So if I were to draw a line straight down, my 0 on my derivative graph would lie here. So it's going to cut the x-axis at 0. Same thing for this 0, which is quite close there, somewhere about here. And my last 0, if I were to bring it straight down, this is where it will cut my derivative graph. So that gives me some valuable information that tells me where I'm cutting 0, or where the gradient will be 0 on my graph. I then need to, if the tangent is positive, y values will be positive, and the converse is true, or in other words, if it's negative, y values will be negative. So if I have a look at this side of my 0, I can see that my gradient is positive. And remember down here, my y-axis represents gradient. So y has to be positive on the left side of this 0 here. So the graph should look something like this. It'll be coming down, where y are all positive values. After my 0, y then becomes negative down here. So between the first turning point and the second turning point, my line must be below 0 on the y-axis. So in other words, it must be down the bottom here underneath the 0, or underneath the y equals 0. I then go positive leading up to my next turning point. So between the second and third turning point, my line must be above the graph, or it should look something like this. And then lastly, my gradient is negative, or the y values must be negative after this last turning point. So that is how I'll draw my graph. So this would be my f of x, or my function. And this one down here is my derivative graph, or my gradient function, my f dash of x. Okay, so that's essentially most important parts are first marking or following these 4 steps. So marking on your graph where positives and negatives are. You then mark your zeros onto your derivative graph, and then you look at, well, what's the graph doing between each of those zeros, so you know whether your line must be above or below 0. Perfect. Good luck with 601. Good luck, Doyle.